And gentlemen, today we're going to continue talking about the measurement part of Unit 1 as we are progressing our way through the unit in Unit 1. I believe this is where we left off last time, correct?
Yeah.
And therefore we kind of added a few things that not all of these are necessary. Ones that you will probably want to know: mega, kilo, centi, milli, and micro. Okay? Now, those ones, that doesn't mean that mastering chemistry won't have you convert to any of the bigger, smaller ones. Okay? It's just for me and purposes for my class, I don't really tend to go to the extreme on making you memorize that peta or peta is that much bigger. It's like 100 or whatever billion it is. Okay? Or quadrillion. Those are small, insignificant things, ultimately. The ones that you will come in contact with more likely inside or outside of in their everyday life, definitely kilo, centi, and milli. Why? Because there's a kilometer. You have kilometers per hour. How fast you're driving in most countries. Centimeters is a common form of measurement. Millimeters is a common socket size or pencil lead size. If you're dealing with a 0.5 or a 0.7 lead or tip on a pen, they're actually dealing with 0.5 or 0.7 millimeters. Okay? So that connection is why I think those five tend to be the ones that you would need to worry about the most. Now, those of you that are in the kind of computers and stuff like that, you already have an inherent knowledge of how big a terabyte is. It's the same thing. It's 1,000 times bigger than a gigabyte. Okay? My first computer was measured in megabytes. It required multiple floppies to start up. And when I say floppies, I'm talking the big 5.5 inchers, not the little 3.5 inch ones. When we got the 3.5 inch floppies, our computer had a big enough hard drive that it didn't require that. So it is a thing. And now our phones have easily a couple gigs, if not almost a half a tera. It's just all depends on how big of a micro SD card you can put in your phone. Some measurements. Common ones that we will be doing either in class, and that is the length and mass. Length is the distance between 2 points. Should be pretty straightforward on that. How do we measure length? Usually the meter, sometimes centimeters, sometimes millimeters. You use the size or the base unit meters and then add a prefix, centi, milli, kilo, to determine how big that is. A lot of times, a common one is usually pretty easy for many of the cross-country runners because we run a 5,000 meter course. Might sound like a lot. Okay, so let's just call it a 5K. It's the same distance. You've just put the prefix of the K in front of the meter, and now it's 5 kilometers. It's the same as saying 5,000 meters. Or you could say 500,000 centimeters. Then you really look impressive. But it all depends on that prefix. And those prefixes are used very readily. You're driving your car. You look at your speedometer. It's usually going to have miles per hour as the big dial in the US. But there's another underneath it, usually kilometers per hour. Why do manufacturers do that? So they can sell their cars in Canada and or other countries. So then they don't have to make multiple things like that. Smarter way of manufacturing. 100 kilometers per hour sounds like it's very fast, but it's only 62 miles per hour. Speed limit probably is about 25 meters per second. It's about 55, 60 miles per hour. And a lot of that comes with converting, which we will talk about later. The big thing also then becomes mass. It's the amount of matter something contains. We, a lot of times, will want to confuse or use terminology for mass and integrate it with weight. But it's not the same. Mass does not change based on location. Not meaning like if I'm standing here in the front of the class, and then I walk to the back of the class, my mass hasn't changed any, but also the gravitational pull hasn't either. To change my gravitational pull, I have to make a bigger significant change in my location than just the front of the classroom to the back of the classroom. You got to change your location by usually 15 to 30 degrees. Latitude and longitude helps. Farther north you get, the difference in gravity as opposed to the equator. Weight will change based on location because of gravity. Usually the easiest one that we tend to give you that is if I weigh 160 pounds on Earth, I will not weigh that much on the moon. The moon has about an eighth of that of gravity of Earth. So my weight would drop significant. Temperature is another one. And that is one that usually causes some confusion. This is one that I think isn't that big of a deal. It's pretty easy for the most part. By definition, temperature is a measure of the average kinetic energy of the particles. We've talked about that before. It's how phase changes happen. Now, how you measure it depends on actually whether or not you're in like two countries or not. Or are you doing it more for science? The majority of the world, all but basically 2 or 3 countries, use the Celsius or the centigrade scale. The Fahrenheit scale is used very rarely in the world. And then you have the Kelvin scale, which is based more for science, based on the idea of absolute zero. Now, the Celsius scale, or the centigrade scale, was not actually done in that manner. And why is Fahrenheit scale different than the Celsius scale? It was actually based on what they were using as their 0 point. The Fahrenheit scale doesn't use water as its 0 point. It actually uses salt water as a 0 point. Salt water freezes at a lower temperature. Celsius uses water as its 0 point. And then just says everything else, and then the boiling point was its 100, and then just kind of said, and then just scaled it out after that. Although they actually had it backwards when it was originally proposed to the French Academy of Science. 100 was the freezing point, 0 was the boiling point. The French Academy of Science looked at that and said, that doesn't make sense. So they flipped it. And now we have the Celsius scale. The Kelvin scale, again, is based on the idea of absolute 0. Now, the conversion between the two isn't too bad, between Celsius and Fahrenheit, if you know a few things. You can use this 5/9 and 9/5 plus or minusing 32, but I think life can be so much easier. Because when you're out and about and you are dealing with things, you will find yourself not having you have a calculator now because it's on your phone, but you might not remember that it's 5/9. Okay? We'll use some easy math for you. Room temperature usually is about 70 degrees. Okay? $70 minus 32. Rough guesstimation. $70 minus 32. Oh, let's do the math. 70 minus 32. 168, right? Divide that by 2 or cut it in half and we get 19. degrees Celsius. You might be off just a little bit, 1 or 2 degrees, but very rarely do people truly are able to feel that difference. Or maybe say you're in a foreign country and they're like, oh, it's going to be a scorcher out there. It's going to be about 30 degrees Celsius. And you're thinking to yourself, 30 degrees is a scorcher? Double 30 and you get 60. Add 32 and you get 92. Ah, that's pretty warm. You might, again, be off a little bit, but it's math that you can do in your head a lot easier. The Kelvin scale are just plus or minus 273.15 is what you go with. And that is, and 0 Kelvin is referred to as absolute 0, the lowest possible. I believe in recent history, we've actually been able to go below absolute 0. And that's, some people ask the question, why would somebody even care? Because in a way, scientists are the greatest deviants, straight from the norm. Now, as the example, usually in the school, if I put a 4-foot wall in the middle of the hallway that allowed people to pass on either side of it and said, whatever you do, don't jump over this wall, I guarantee people are going to jump over the wall. Why? Because it's there and they're told not to. Oh, you can't do that. So they do it. One, they want to see what the repercussions are. Science is the same way. You can't go faster than the speed of light. Well, why can't we try? Let's try to do that. Let's figure out ways to try and push that envelope. You can't go below absolute zero. Well, why don't we try and see what the repercussions are? Validating other things. Pushing the envelope. Man will never be able to fly. Oh, look, Wright brothers. Figure it out. And within 50 years of that, flight becomes fairly almost commonplace. Doesn't take very long for things to start catching up once you find out what you can do. And that's why do we say as low as possible? Yeah, it is for now. Someone's probably going out there trying to figure it out how to do it even better. Volume is another one that sometimes gets people. It's how much space that matter occupies. Common one that we use in the laboratory, and this is a very common laboratory one, is the liter. But we really use the milliliter. Now the milliliter a lot of it is based on a centimeter cubed. That's why in some line of work, they don't call it milliliters, they call it cc's. And that becomes the 1 milliliter is the same as 1 cubic centimeter. It's the same. It's an equivalent. How many milliliters are there? It's the same as how many centimeters cubed there are. Some graduated cylinders, usually 10 milliliter graduated cylinders, are so well spaced out that they can even be put on their side and used as a 10 centimeter ruler. Not all of them, though. And it's because of the way in which their cylinder is spread out that you could almost use that height aspect of the cylinder as 1 centimeter per milliliter as it goes up. That's because the cylinder, because it's got that circular part, is taken into account. What gets a lot of people is they think that a liter then is a meter cube, but a meter cube is very, very massively large. I always use the example, it's about the size of a dryer. That's a meter cube. That's a fairly large item. Your washer is probably almost the same size. It might be a little bit less, but it's about a good approximation. Because a meter is about 39 inches long. And so it'd be 39 inches by 39 inches by 39 inches. That's gets to be pretty big. A liter is the equivalent of a decimeter. Decimeter. Which is, you're like, well, that's a decimeter is like 10, and a centimeter is 100. Why are they so close? And a milliliter and a liter are 1,000 apart. That's because you have 10 times 10 times 10. 10 times 10 times 10 is 1,000. That's where your difference between a milliliter and a liter come into play. between a centimeter and a decimeter, the difference is 10. But on a cube, as we kind of see here, you have one side, and then back. And so it's not always exact. So the cube, because you have to multiply with that and how that works. And sometimes that 1 centimeter, especially in other lines of work, it's called this. cc's, cubic centimeter. If you ever watched the doctor show, I need X number of cc's stat. They could just say I need this much milliliters, but they go to school for gobs of money, so they want to say cc's. And stat. Everything's got to be stat. But it's the same thing. It's the same measurement. Which then brings us to our first derived measurement, and one that we use here is density. Now, I've seen different reference materials that have density not as a lowercase d. I've seen it as like a p before, but I don't like that one because that one I use for momentum in my other classes. Normally, units for density are grams per milliliter. Grams per milliliter. For gases, because they take up much larger spaces, they are usually reported in grams or kilograms per cubic meter because they need so much more space. Now, one of the nice things with this is a lot of times we're going to use water and the density of water because, as we'll find out, the density of water is about 1. Okay? We're going to just round it to a nice even number of 1. That means 1 gram is 1 milliliter because the equation, mass divided by volume, if I say the density is 1 gram per milliliter, that's the same as saying that fraction the same way. 1 gram per milliliter. Because 1 divided by 1 is what? 1, right? If I had 2 divided by 2, it would also be 1. That means if I had 2 grams of water, I would also have 2 milliliters of water. Because the density of water is 1. It's in a 1-to-1 ratio. And that becomes extremely useful for us in the lab. So the density, and that's an equation that we'll use. It's an equation that you'll want to have. Hopefully you wrote that down somewhere. Now, again, you don't need to write all of that information down because it's just kind of show you that not everything has the same. Not all numbers or not all objects have the same density as, say, water does of 1. And we know this shouldn't be a thing because we always use this saying, does oil and water mix? No, they separate. The fact that oil and water are not mixing doesn't have anything to do with their miscibility. And what it does have something to do with is the fact that they have a difference in density. You can have objects that have different abilities to mix, whether they're miscible or not, they mix, because ethanol and water have different densities, but when you mix them, they don't form different layers. They're miscible. They mix. Oil and water are immiscible. They don't mix. They form layers because of their density. Wood floats on water, usually, because it's immiscible, doesn't mix, and has a lower density than water does. Things that sink, me in a pool, I am not miscible, but my density is high, so I sink. I don't float very well. Some of it might be due to the fact that I have a tough time relaxing or I'm always stressed. Remember, density is also a physical property. It's one of the Yoda properties. It's an intensive property, meaning size doesn't matter. The amount of matter that you have is just going to take up less or more space, because the ratio in which the mass to volume is gives you the density. A small little turning of copper has the same density as a whole big roll of copper, because that big roll of copper has more mass and takes up more space. You would think, oh, it's got to have a higher density. No, it's the same, because it's the mass to volume ratio. The amount of mass that little copper turning has is smaller, and therefore also takes up less space, therefore has the same ratio. That's how they are able to determine whether or not something has gold, based on the density. So let's try some examples of calculating density out. Density of mercury. What is the density of mercury? 1 times 10 to the second grams. That occupies a volume of 7.36 centimeters. When I do a lot of these math things, I usually like to do them very step by step, which means I will take and go mass is equal to 1.00 times 10 to the second grams, which some of you might prefer to have written as just 100 grams. The volume, writing down my knowns and unknowns, is 7.36 centimeters cubed. I'm asked to solve for density. The density equation mass divided by volume is that. We have the ability to now add our knowns in. If I keep my labels present, the label that I need for my answer is given to me. And that now all I need is a calculator, and I prefer to have students use and or have their own ACT approved calculator, since you'll need to use one probably at some point. And we find that the answer, by doing the division, is 13.56. Is it 7? Let's go 3 significant digits. 5.6, 13.6 to the proper number of significant digits, with a label of grams per centimeter cubed. So here we have another example. This time we're solving for volume, and we are asked to remember the density of ethanol. And so we write out what we have here. Again, always writing out what we have to help us out. And the mass is 65 grams. Volume, in this case, is unknown. The density, if my memory serves me right, is 0.79 grams per milliliter, or it would be also written as 0.79 grams per centimeter cubed. The density equation hasn't changed any, and so mass divided by volume. Here we have our mass. We plug it into our equation. Solving for volume equals our density. And so here we need to solve for V. Some of us that are a little more experienced at algebra will know that I need to multiply both sides by V so that the volume, not velocity, cancels out algebraically, then leaving me with the equation of volume times the density of 0.079 grams per milliliter is equal to 65 grams. Now, those of us that have done algebra before also remember now I need to divide both sides by 0.79 grams per milliliter. Those two cancel out or make the ratio of 1, depending on how you want to look at it. And that should give us then what we need to solve for volume. So 65 divided by 0.79. Now we take that and punch it into our handy dandy ACT approved calculator. And we get a bigger number, which should make sense because it's, a number divided by a smaller number will give us a lower number. And our answer is 82.3 milliliters. The last example we have is what is the mass in grams of a cube if the length is 2 centimeters. This one usually gets students because we have to think about some things. We don't have a volume per se. We don't have a mass either. Gold, if my memory serves me right, is about 19.8 grams per milliliter, or 19.8 grams per centimeter cubed. What I do have is I have a side or a length, and I also am told that it's a cube. Because of that, that gives me some information and I remember that volume can equal length times width times height. And since we're dealing with a cube, all three sides will be the same. With that in mind, I would take 2 and cube it. Not cubert, cube it. And so if I take 2 and cube it, I will get 8. And that would be centimeters cubed. So therefore, I do have a volume of 8 centimeters cubed. Given that the density equation, again, hasn't changed much at all, mass divided by volume, we can solve for what we need. Because in algebra, you can solve for things. Sometimes you just have to find things to solve for things. And that's what we do. So I take my 19.8 grams, and since I have the volume in centimeters cubed, I'm going to use that same one in centimeters cubed is equal to the mass divided by volume. I need to now multiply both sides by 8 centimeters cubed. By doing that, those ratio out to 1. My labels on the other side will ratio out to 1 or cancel out. And I now have the equation of 8 times 19 grams, meaning I'm scaling it up by 8, is going to give me my mass. So again, using my ACT approved calculator, I punch in 19.8 times 8 to give me an answer of 158.4 grams. There we have the examples for how to solve for density.